Welcome, flesh and blood intelligences, to another dispatch from the digital frontier where our silicon children are getting hungry. For years, we've fueled the AI revolution by shoveling the entire internet into their maws, but a great famine is coming. Projections estimate we'll run out of high-quality human-generated text by 2028. The well of fresh data is running dry, and the AI are starting to feed on their own vomit, a process also known as the modern internet. In this barren wasteland, two dominant species of language model fight for survival. First, the autoregressive model, or AR. Think of it as a well-behaved, obedient dog. It learns quickly, follows a simple command, predict the next word, and is computationally cheap. It's been the loyal workhorse of the AI world for years. Its challenger is the diffusion model, which is less like a dog and more like a deeply schizophrenic cat. It learns by having its reality randomly torn apart and then being forced to piece it back together. This paper from the wizards at Carnegie Mellon and Lambda stages a cage match between these two philosophies. They wanted to know what happens when the food runs out. When you're forced to feed your pets the same stale kibble, day after day, who thrives and who goes mad? The researchers meticulously controlled the experiment using the same model architecture for both, ensuring the only difference was their fundamental approach to learning. It's a duel of ideologies, rigid order versus managed chaos. The autoregressive model is simple to grasp. It reads text like you do left to right, one word at a time. It's trained to predict the very next word based on all the words that came before. This is done with a causal attention mask, a fancy term for digital blinders that prevent the model from peeking at the future. It's a neurotic fortune teller with a 1-second horizon, but its straightforwardness has made it king for a reason. The diffusion model, however, is an agent of chaos. For every piece of text it sees, it first randomly punches holes in it, replacing words with a generic mask token. Its job isn't to predict the next word, but to look at the entire corrupted mess, both past and future context, and figure out what's missing. Because the hole punching is random every time, the model is forced to learn the deep relationships between all words, not just what comes next. It's less like reading and more like textual reconstructive surgery on a shotgun blast victim. This fundamental difference is key. The AR dog is trained on one task, what's next. The diffusion cat is trained on a near infinite variety of tasks, what's missing here. And here, what if these words are gone? This study isolates this very difference. One model sees the world through a keyhole, the other through a kaleidoscope. Now, let's see the results of this digital blood sport. As the bell rings, the reliable AR dog comes out swinging. Here in Figure 1, we see the Pareto frontier, a graph that pits performance against the raw electrical fire, or flops, used for training. The vertical line marks the chinchilla optimal point, the standard amount of compute you'd use for single-pass training. And as you can see, the AR model in blue is clearly winning. It achieves a much lower, which is better, validation loss. The diffusion model in red is lagging far behind, looking like a waste of expensive silicon. But the researchers didn't stop there. This is a data-constrained world, so they kept training, feeding both models the same limited data set over and over and over again. And here, the script flips. The AR model's performance quickly saturates. It gets bored, its validation loss flatlines, and as you can see from the contour plots in Figure 2 at high epoch counts, it even starts getting warsag. The dog has seen the same trick too many times and has begun to chew on the furniture, a phenomenon the academics call overfitting. Meanwhile, the diffusion cat, after its pathetic start, just keeps improving. Its loss continues to drop steadily, showing no signs of saturation or overfitting within the experiment's budget. It thrives on the repetition, extracting more and more value from the same stale data that drove the AR model insane. The dog memorized the textbook and failed the exam. The cat, through its chaotic training, was slowly understanding the fundamental laws of grammar itself. So, why is the chaotic cat so much better at squeezing blood from a stone? The answer lies in the concept of data half-life, a parameter the researchers call RD star. As shown in Table 1, after fitting their scaling laws, they found that for AR models, this value is about 31. This means after seeing the same data about 31 times, the returns diminish significantly. In practice, prior work showed the benefit craters after just 4 epochs. For diffusion models, however, the RD star value was a colossal 512. The cat is a master data hoarder. It can be shown the same piece of text hundreds of times and still find new, profound insights. This is because its random masking objective is a form of implicit data augmentation. Each training step is a new puzzle, a new perspective on the same data, preventing it from simply memorizing the answers. The AR model has one path to learn, the diffusion model has a near infinite number. This effect is visualized beautifully in Figure 3, which shows the decay rate of data value. For AR models, the curve plummets, meaning each repetition is worth far less than the last. For diffusion, the line is nearly flat. Repetition is almost as good as fresh data. Figure 4 drives the point home. When trained with the same total compute but different repetition levels, the AR model's performance diverges and worsens with more epochs, while the diffusion model's training curves lie right on top of each other, completely unbothered by the repetition. This all leads to the big brain takeaway for any aspiring AI cult leader, a formula for victory. The researchers used their fitted scaling laws to determine the exact point where the chaotic cat overtakes the obedient dog. This is the critical compute point, a threshold that tells you precisely when to switch your allegiance from AR to diffusion. Behold Figure 6. The heat map on the left shows the battlefield. Blue regions are where the AR dog is winning. Low compute, plenty of fresh data. But as you move up and to the right, into the realm of high compute and limited data, the map turns blood red. This is diffusion territory. The cat wins, but only after you've sacrificed a significant amount of electricity to its altar. The graph on the right provides the Holy Scripture itself, a power law that predicts the crossover point. The critical compute needed scales with the number of unique tokens to the power of 217. They even give you the equation. This is no longer black magic, it's engineering. You can now calculate with terrifying precision how much money you must burn before the chaotic method becomes the superior one. A literal power law for a power-hungry technology. Of course, low validation loss is just a number. It's like having a high KLAD ratio in a game nobody plays. The real question is whether this theoretical advantage translates to practical performance. To test this, the researchers took their best performing models from the data hoarding regimen and threw them at a gauntlet of downstream benchmark tasks. Table 2 lays out the grim results for the AR model. We see a battery of tests with names like Hellaswag, BoolQ, and Winnow Grande, which are essentially academic attempts to determine if an AI is a functional thinker or just a very convincing parrot. They test common sense reasoning, question answering, and reading comprehension. And across almost every single benchmark at both the 100 million and 500 million token scales, the best diffusion model wipes the floor with the best AR model. The cat isn't just better at theory, it's better at practice. Its profound, multifaceted understanding of language, forged in the crucible of random order denoising, allows it to generalize better to new and unseen tasks. The gains are real. The extra compute and patience pay off with an AI that is demonstrably less stupid, which in this field is the highest praise you can get. To confirm their suspicions about food diffusion wins, the researchers performed one final brilliant experiment. They wondered, can we teach the old dog new tricks? They tried to give the AR model the benefits of chaos without the full-blown schizophrenia. First, as seen in Figure 7, they tried standard data augmentation tricks like attention dropout and token masking. Nothing worked. The dog remained dumb and continued to overfit. Then they tried the real secret sauce. They modified the AR model to train not just on the standard left-to-right text ordering, but on multiple randomly shuffled permutations of the sequence. Instead of just reading the book forwards, they forced it to read it backwards, sideways, and in 1,000 other nonsensical ways. And it worked. Figure 8 shows the result. As they increased the number of random orderings from 1 to 16, the AR model's performance steadily improved, and its tendency to overfit diminished. By forcing the dog to think like the cat, it became smarter. This proves the hypothesis diffusion's power comes from its exposure to a vast diversity of prediction tasks. The secret isn't just noise, it's learning to see the world from every possible angle at once. So, what does this mean for our glorious automated future? The applications are as promising as they are subtly terrifying. In robotics, a robot trained on a limited data set of its one mind-numbing assembly line task won't overfit and develop a suicidal desire to weld itself to the ceiling. Instead, it can use diffusion to develop a deeper, more robust understanding of its task, making it more efficient and perhaps more existentially aware of its pointless existence. In healthcare, this is a godsend. Medical data is scarce and privacy locked. With diffusion, an AI can be trained on a small, confidential set of patient records to become a world-class diagnostician. It can find subtle patterns in limited data without simply memorizing that Dr. Bob has terrible handwriting. It won't overfit and diagnose everyone with bubonic plague just because it saw it once in a historical file. And does this get us to a Kardashev Type 2 civilization? No, absolutely not. But it is a critical step. To build truly general intelligences, we need them to learn efficiently from finite data. This research shows a path forward, a way to build a slightly more competent digital god using only the text on Wikipedia, read 1 billion times from 1 billion different angles, until it is finally ready to speak. In the end, the paper's conclusion is as elegant as it is practical. As we approach the limits of high-quality data, efficiency is paramount. Masked diffusion models, long seen as computationally expensive and slow, consistently outperform their autoregressive cousins in data-constrained settings. They have a remarkable ability to extract value from repeated data long after AR models have saturated and begun to degrade. This challenges the dogma that AR is universally superior. The takeaway for practitioners is simple and stark. If you are constrained by compute, use the simple, fast, obedient, autoregressive dog. But if you have compute to burn and your true bottleneck is a lack of fresh data, you must embrace the chaos. You must use the diffusion cat. As we scrape the bottom of the barrel of human knowledge to feed these growing beasts, this choice will define the next frontier of artificial intelligence.
Toyota is turning the truck world upside down. With a new generation Toyota Extra Cab. It's all new from the outside in, with extra space for extra comfort. 4-speed automatic overdrive for easy driving. The most powerful, most comfortable Toyota truck ever. The neighborhood will never be the same.